大家好，我是Chao. Hello, everyone. I'm Chavis Von Bradford. Today, I want to take you through a deeply troubling line of reasoning regarding the nature of our universe. The researchers whose work I am presenting begin with two assumptions that are widely considered well motivated. First, that our universe is headed for a final flat decenter phase driven by a cosmological constant, which was discovered by Albert Einstein as a mistake. And secondly, that the principles of holography and horizon complementarity, which have been so successful in describing black holes, apply to cosmology. The objective here is not to solve the puzzle of the universe's low entropy beginning, but to sharpen the question. The key is to find that these seemingly innocuous assumptions lead to very profound paradoxes, and they force physicists and mathematicians alike to conclude that our universe is a statistically unlikely fluctuation, and that our universe is a rare bubble of order in an eternal and mostly featureless sea of thermal equilibrium. Now, to navigate this argument, we need to define a few key concepts that we will be talking about over and over again in this particular video. We will talk about the causal patch, which is the region of space-time that an observer can ever influence or be influenced by. This is the only region we can operationally describe. Another term will be horizon complementarity. And this is the idea that the description of a region bounded by a horizon is self-contained and that it is a closed quantum system. Finally, we will be talking about the famous Poincare recurrence. And it is a theorem stating that any finite isolated quantum system will, after a sufficiently long time, but a finite time, return arbitrarily close to any given initial state. This concept becomes central when we consider the universe as a finite system. Now, the story begins with a well-known puzzle. Cosmological evidence suggests an inflationary beginning and an accelerated decenter-like end of the universe. Yet the initial singularity is not well understood. The Transplanckian problem for inflationary fluctuations and the idea that the seeds of the structure that originated from the modes with wavelengths shorter than the Planck length mirrors a problem in black hole physics. In both cases, the remedy inspired by black hole complementarity is to restrict our attention. Instead of trying to describe the entire global spacetime, we should focus only on a single causal patch, treating it as a closed finite box with the observer at its center. And this is kind of ironic because you're thinking inside the box. This perspective transforms cosmology. If the universe has a positive cosmological constant, its causal patch has a finite entropy given by the area of its horizon. A finite system, if left alone for a long enough period of time, will have a kind of equilibrium. But because it is finite, it will also experience Poincare reoccurrences. And you can consider a box of gas and its final entropy on what is quantified with S, and on time scales on the order of e to the power of S. The gas will spontaneously fluctuate back into a low entropy state, like all the molecules have gathered back into a particular corner of said box. The researchers argue that this is a model that we must consider for our universe. And the standard history of inflation and the reheating after the fact and the matter domination after that would then be a brief, rare fluctuation away from thermal equilibrium, after which the system slowly returns to its featureless final state, only to do it all over again. Now, the central quantity of the entropy of the causal patch in decenter space has very particular mathematics. The entropy is the fundamental measure of the size of the system's Hilbert space, and it is the ultimate source of the problem. Now, this equation states that the entropy, S, is equal to the area of the horizon, which is 4 pi r squared divided by 4 times Newton's constant g. Here, r is the inverse Hubble scale, the radius of the de-Sitter horizon. And for our observed dark energy, this yields a staggering entropy on the order of 10 to the 120. Now, this number is a logarithm of the number of possible quantum states in a causal patch. The key part of the analysis involves constructing a gauge invariant Hamiltonian for the causal patch. In a simplified 2 plus 1 dimensional model, the researchers show that the total energy of the system in a carefully chosen particular gauge is constant and independent of the matter content. This is the Hamiltonian in their observocentric gauge. Let's get into this. It is the integral over the spatial coordinate rho and the angle theta of several terms. The kinetic and gradient energies of the metric functions of z and v, and the kinetic and gradient energies of the scalar field phi and its potential v. This Hamiltonian is constrained by the Einstein equations so they can equal a fixed number, which is 2. In their units, they are demonstrating that all complex cosmological dynamics happen at a fixed total energy. The consequence of this finite system is the reoccurrence of time. The time it takes for a fluctuation to recreate an inflationary state from the equilibrium of the dead flat de-Sitter space that is determined by the entropy difference. Now, there's another equation, and this expresses the reoccurrence of time on various scales. And it pretty much shows that the typical time for a fluctuation, T sub r, is on the order of the exponential of the equilibrium entropy S minus the entropy S prime of the fluctuation itself. For a high scale inflationary state, S prime is about 10 to the 10, while the equilibrium entropy S is 10 to the 120. This yields a reoccurrence time that is roughly about 10 to the 120, an astronomically long time compared to the age of our universe. Just going off script here, the um, universe is kind of projected to really reach a so-called final equilibrium state in about 10 to the 10 to 100 and some years. So this is even after that. But this is not the problem itself. It simply means that our universe is a rare event. Now, the profound paradox emerges when we consider the probability of our specific universe. The entropy of the observable matter in our universe today is about 10 to the 100. And these particular researchers argue that the number of microstates consistent with a world like ours is exp 10 to the 100. The crucial point is that the vast majority of these states are all about exp 10 to the 10 of them could not have evolved from a standard low entropy inflationary beginning. They would have to arise from a much more common miraculous fluctuation, if you want to use that word, directly out of thermal equilibrium. For example, one could imagine a fluctuation that yields a universe that looks just like ours, but with a cosmic microwave background at 10 degrees Kelvin instead of the one that Penzias and Wilson observed at 2.7 degrees Kelvin. Now, such a world would be vastly more likely to occur via Planck recurrence than our own, simply because there are so many more ways for a thermal system to fluctuate into that particular state. The researchers call this a somewhat misanthropic conclusion, in that a recurrent universe like the de-Sitter space of our universe with its consistent low entropy history would be extraordinarily unlikely and vastly outnumbered by the peculiar and incomprehensible worlds that nonetheless support life, and making it where I'm able to make this video. Now, let's analyze this paper. We can't just take any paper at face value. So let's analyze the strengths, weaknesses, opportunities, and threats when it comes to this paper. Now, the strength is its logical consistency. It starts from a well-supported assumption on the cosmological constant and the horizon complementarity, and its conclusions follow with a near mathematical certainty that I stated before. And it unifies puzzles from black hole physics with cosmological singularities and things of that sort. But a critical weakness is the very nature of its starting assumptions. The application of horizon complementarity to a de-Sitter space is an assumption, it's not a proven fact. There is no fully understood non-perturbative quantum gravity theory of de-Sitter space, unlike for anti-de Sitter space. The framework is built on a very speculative foundation. Now, there is an opportunity here. The paradoxical conclusion forces physicists and mathematicians to re-examine our most fundamental theorems and our hypotheses and models. And it suggests that the observed dark energy might be a cosmological red herring. Perhaps the only reasonable conclusion is that we do not live in a world with a true cosmological constant. The pressures this pressures us to find a mechanism for dark energy that can decay, or to develop a theory where the universe is truly infinite and not a finite box. The most significant threat to this paper is this viewpoint that it may be somewhat self-defeating. If the vast majority of self-aware observers find themselves in these miraculous universes of that are seemingly inconsistent, then we as observers should not expect to find ourselves in one. The fact that we do not, and that our universe appears so orderly and has this coherent thermal history, is an inconsistency that threatens the entire logical framework. It implies that either the assumptions are wrong or that we are missing a crucial element that picks out conventional histories rather than viable ones. So let's get into some gaps, some various kind of gaps in knowledge and empiricism and things of that sort. So the clear empirical gap is that we have no experimental access to these timescales of 10 to the 120 years. Okay, there's no way to test that kind of statistical prediction at this time. Maybe there will be in the future. There's an implementation gap which lacks a concrete non-perturbative dual quantum theory for de Sitter space that would make the finite system claim rigorous. There's a knowledge gap that exists in our understanding of whether a system with a finite Hilbert space like the one that they propose in this paper can be truly ergodic. And I think Sean Carroll talks about this in a way that makes the statistical arguments valid. There's a contextual gap in the failure to integrate this perspective with the standard successful model of cosmic inflation. Inflation was proposed to explain the universe's low entropy, but here it is itself a fluctuation that requires deep explanation. And pretty much there's an evidence gap at the heart of cosmology. We still lack a fundamental quantum gravitational explanation for the initial conditions of the universe that are before the GUT era and the electroweak era and the inflationary era. Something near the Planck era regime where we can describe things based off of both general relativity and quantum mechanics.